Hello. Here we discuss total internal reflection. This is a consequence of the law of refraction in the extreme sense. So let's see what this is. So we have a surface, an interface, and let's say on one side we have air. So it's N1 is equal to two sig digits. Actually, we're working three sig digits. So it's to three sig digits, and one is pretty much one. As far as it's air, up to about four or five significant digits, it's one stays one. So that's air. On the other side of the interface, we have benzene, which has a refractive index of 1.80. So it's benzene. 1.80 means that the speed of light in benzene is 1.8 times smaller than the speed of light in vacuum, which is basically air to to three digits. Let's have a reference line which represents our normal ray. So that's our, oops, like a straight line. So that's our straight line perpendicular to the interface, and that's will be our normal line. Let's have some blue lines. Let's begin with this here, and that's my reference line. Actually, I should go only to here. So, so that's my ray that comes in. But now, law of refraction says that instead of actually going in a straight line down here like this, that's what we would expect if not for the interface. Light travels in a straight line. It should go straight, but instead it actually bends away from the normal when it goes from denser to rarer. So this is benzene is denser because the speed of light is smaller inside benzene, or refractive index is larger. So instead of going straight, it can either go bend towards the normal or away from the normal. When it goes from air to benzene, it will bend towards the normal. But now we are going from benzene to air specifically to see an effect which is called the total internal reflection. So the ray from here on bends a little away from it, so that's down there. Right? And how much away is decided by the ratio of 1 to 1.8. So that's significantly large, so it's about two times, and it is a sign of the angle that's coming in. So that's this point in here. So, so let's say that's our refractor. Let's have another ray of light coming in, originating from another point inside the medium. It's not at the same point, not along the same line connecting the interface point we are checking on with this. Now, since the incident angle is larger, the angle of refraction will be larger, and this will be significantly larger. And as we proceed, we notice that after a certain point, or after a certain limiting scenario, there is no room on the refracted side. It, in fact, at this point, grazes uh, the interface at all, which means that now if I were to draw one more line from here, there is no room there. Like, it cannot actually get reflected. So let me label these rays so that you have a clear picture of what's going on. So this is ray 1, and after refraction, this is ray 1. That's ray 2. After refraction, it goes in here. So that's your ray 2. That goes here. Ray 3 is actually the limiting scenario where it barely graces the interface. So that's 3. And 4 cannot go beyond that. So 4 doesn't exist. So 4 uh, does not refract. So the energy does not go into the air at all, but it will still reflect. It can, all these rays can reflect also, right? So maybe I should point that out clearly. So maybe clarify that each of this ray has a reflection part also. So that's your reflection angle of incidence is equal to angle of reflection. So that's 2, that's 3, and that's 4. So labeling them again. So it's reflected part of the incident ray are these. So the 4 rays that we have picked to choose, the many rays, after touching onto this particular point, all 4 of them reflect, but they do not refract. Only 3 of them refract, and fourth one only manages to reflect. So the point is that after this critical point 3, so there is a critical angle, which here we have chosen is, this is the critical angle, beyond which there is no refraction, only reflection. And that's what is total internal reflection. As far as the calculation goes, it is very relatively simpler, because for this critical angle, the angle of refraction is 90 degrees. So for the ray that has angle of incidence as theta critical, angle of refraction, so let me call it theta r, refraction is equal to 90 degrees. And sine of 90 is 1. So law of reflection is governed by Snell's law, which is n1 sine of theta 1 is equal to n2 sine of theta 2. And plug in the numbers. N1, that is the numbers in the air. N1 is 1.00. What's the angle of uh, what's the angle in air? That is the angle of refraction. That's 90 degrees. So it's sine of 90 degrees. And 2 is that of benzene. And sine of theta 2 is the critical angle we are interested in. Sine of 90 is 1. So sine of the critical angle is 1 over 1.80. So the critical angle is equal to sine inverse of 1 over 1.80. And that's 3 sig digits. It is 33.8 degrees. Let me stop sharing here and let me stop the recording.